Okay, so in this lab, all we're doing is confirming that Newton's second law works the way we think it works, okay? And that is that acceleration is related to the net force acting on a system and the mass of the system, okay? If the mass of the system doesn't change and F net increases, what should happen to acceleration? Bigger F net means bigger acceleration. That's what Newton's second law says. That's what we're investigating today with this lab, okay? So, here's how this lab is going to work. And if you listen carefully, you'll probably get most of the variables, right? I'm not going to outright say the manipulator variable is this and whatever, okay? But I'm going to go through the design here. So, what we're going to be doing is we're going to have a setup that looks like this. We'll have our carts that have all the sensors in them. They'll be tied, there'll be a string tied to them, which will go over a pulley to a hanging mass, okay? This hanging mass is going to supply the applied force, or net force, that will move this system, that will accelerate this system, okay? So the lab will work as follows. I'll have the cart with some masses on it, and then I'll have a hanging mass. On my first trial, I'm just going to have 50 grams hanging over the pulley. On my second trial, I'm going to take 50 grams off the cart and move it over the pulley. Okay? When I do that, that's going to change the applied force. I'm going to do 4 different trials with 4 different applied forces. I'm going to measure the acceleration that each one of those applied forces produces. I'm never going to add or take away mass from the system. I'm only going to change where in the system that mass is. Okay, that's really important because, as we know, the mass of a system can affect, okay, the acceleration of the system. So all I'm doing is moving the mass around. I'm not actually changing the overall mass of the system. Okay? Now, some other things I'm going to want to watch for, okay, during this lab are that I'm going to want to make sure that my ramp is pretty level. Okay? I want it to always be the same. If it's not, if it ever got inclined or declined or something like that, okay, that could really interfere with it, okay, and that could even be a source of error. Right? We're going to do our best to make sure they're level. You can use your phone for that. Okay? In the measuring app on your phone, if you click on that, one of the 2 things it can measure is level. You just click on level and set it down on its side. It'll tell you whether it's level or not. Okay? So you're going to want to do your best to make sure that your ramp or track is level. Now, one of the things that can happen with the tracks is as the cart moves down the ramp, it can actually cause the ramp to tilt a little bit because the weight gets distributed a little bit differently. There's not going to be anything you can really do about that. You just do your best, okay, to make sure that the ramp is level at least at the start. Okay? You'll know whether that happens based on your results. Okay? Your results will actually scream at you that it got tilted somehow, okay, if that happens, and it's not a big deal if it does. All right, and then obviously we want to try and use it in the same cart, and we want to make sure our track is clean and all of that kind of stuff, okay, is important throughout the procedure. Okay, for our hypothesis, okay, remember, we're investigating what relationship exists between the force that's applied to an object and its acceleration. So the if part should deal with that. In the if part, you should basically tell me what Newton's second law says about an applied force and the acceleration it can produce. What kind of relationship is there? Is it linear? Is it exponential? Is it inverse? Okay? What kind of relationship exists? That should be the if part of your hypothesis. Okay? The and part of the hypothesis describes the experiment. Okay? Several different applied forces will be applied to a system, and the acceleration of the system will be measured. Okay? I mean, that's effectively what's going on here. In the then part, you need to tell me what's going to happen to acceleration as your applied force increases. I don't know what happened to the rest of the word increase. It disappeared. Increases. Okay, so the procedure is going to work like this. You're going to have the ramp, well, not ramp, I keep saying ramp because I don't want it to be a ramp, we want it to be level. So the track, okay? You're going to build the track and you're going to put one of these pulleys on the end of the track, okay? Just these little plastic pulleys. Now they're delicate, but they're also really good. Okay, very low friction. They spin for a very long time after they get going. Okay, they just clamp on to the ramp. Now, Mr. Dickey's class thankfully used these a little bit before us. Okay, and they put on these pieces of meter sticks so you can actually like screw them on here. Okay, you may need to, if you're just using the plastic tracks, you may need to put a little piece of folded paper in there to get it tight. Okay, now the string is going to go over that pulley, and you're going to have a hanging mass over that pulley. Okay, so these are the mass kits here. Okay, they have a bunch of masses in them. And then you're going to have your cart, and there's going to be some masses on the cart. Okay, and I'll go through what the arrangement of the masses will be here in a minute. Okay, but we're going to use those same carts we used before. Okay, you need to make sure that you've got them pointed the right way as they go down the track. This is the front end. Okay, so you're going to tie the string. There's a little spot right here on the very front end. It's just a loop. Okay, you're going to run the string through there and tie a knot. Okay, that'll pull the cart forward. Everybody with me? Okay, this area here on the top of the cart is for putting the masses in. Up here on the red cart is some fun tack. You just need a little tiny bit of this on the bottom of any masses that are sitting in here. Because if you don't put that on there, Newton's first law will apply. And as soon as the cart starts to accelerate, it will slide out from underneath the masses sitting on it, just like the dishes and the tablecloth trick. Okay, so you need to make sure that they're stuck on just a little bit, okay, with the fun tack. Okay, so just a little tiny piece of fun tack on each mass, and they'll stay put for what we need. Okay, so you'll have it just accelerate that way. So on our first trial, and you don't need to write this down because it's actually in the instructions. For the first trial, you're going to have 400 grams worth of mass sitting in the cart and 50 grams hanging over the pulley. Okay? And then each trial after that, you're going to take 50 grams off the cart and hang it over the pulley. Okay? Until you've done 4 trials. So eventually you're going to have 200 grams hanging over the pulley and only 200 grams sitting on the cart. Okay? All right. So that's how that's going to work. Okay? Again, we'll go over that here in just a sec, but that's, okay, in general how that's going to work. For the masses, okay, the biggest thing is that you want to let the cart accelerate as much as you can. Okay, it's only going to accelerate as long as that mass is falling. So once the mass hits the floor, it's done because it's not pulling anymore. Okay, you have to have one person in your group whose job is to stop the cart. Okay, because if they don't, it will hit the pulley and it'll jump over the pulley, wreck the pulley, and then the cart will go flying and crash into the ground. And it happened in period 2. Okay, that's why I'm re-recording the podcast. Things were said. Okay, yeah. So we're not going to do that. We're not going to have a repeat. We're not going to have to say things again. Okay, after that. So make sure there's one person and they have one job. And that was kind of what was said with other things in it. You had one job. Okay, you had one job and you didn't do it. Okay, one person's sole job is stop the damn cart before it hits the pulley and goes flying over the edge. Okay, so please make sure that that person is on the ball. Pick the most reliable person. Maybe have a backup. Okay, yeah. All right. So you got to make sure that that's done. Okay. And again, reaction time and the lag of the app, you need to take that into account. So whoever's starting the app, okay, start it. When you see it starting to go, tell the person to let go of the cart. That way you don't miss anything. And you should have it recording at 20 hertz. Okay, I think the default is 10 hertz. You can change that on there. Okay, but you should probably have it recording at 20 hertz because it's not going to take very long. Okay, it's going to accelerate along there pretty quickly. Okay, so the thing that we're recording with the cart is just the speed, or the velocity, sorry. Okay, that's all we want. We're going to make a velocity versus time graph of each trial, and that'll get us our acceleration. And we need that. The acceleration is what we need for the lab. Okay. All right, So what we're going to be looking at, okay, is this situation here. Now, depending on whether you have a red cart or a blue cart, your mass is going to be different. Don't ask me why, but the red carts are 4 grams heavier than the blue carts. I don't know why. I guess blue plastic and red plastic are different in density. I don't know why, but it's on every single one of them. Okay, so just know that for your first trial, okay, the mass of the cart plus the 400 grams that's on it is going to be 0.670 kilograms. Make sure you record everything in kilograms, because when you do your calculations for force, your mass needs to be in kilograms. Very common mistake. Okay, so make sure that it's all in kilograms. These will be your numbers, depending on whether you have a blue or a red. Okay, those will be your numbers, and this is your hanging mass, okay, over the pulley, okay, for each of the 4 trials. So what you'll need to calculate first is your applied force, which is just whatever you've got hanging over the pulley times 9.81. Okay, easy to calculate for each one. The acceleration is the next thing. That's going to be the slope of the line on each velocity versus time graph. I'll again show you how to quickly do that. Okay, and then your net force is your acceleration from this row multiplied by the mass of the system. Okay, so that'll be this number plus this number. Will you have to do that operation for every trial? No, because what's happening to the mass of the system? It's the same all the time. Okay, so you only have to calculate the mass of the system once. Okay, all right, so that's what you're going to be filling in on there. Everybody with me on that? That's actually the first 3 analysis questions, is filling in that chart and doing those things. Okay, all right. I'm not going to talk about the rest of the analysis questions until we've got data, because I don't want to overwhelm you. Okay, so let's just get our materials: a cart, a mass set, a track, okay, a pulley. There's string in here already. Okay, so you can use that, okay, reuse that, and just put them on the desk. Okay, you might want to push 2 desks together. Okay, they work a little bit better that way. All right. Okay, so everybody's got to be masked up during the data collection, please. Okay, so if you're needing to delete a whole column, all you do is click on this little arrow here, okay, and just delete that column. So for all those ones that are data that you don't need, that's what you do. Okay, if you're looking that you started it early, and then the person let go and you got a bunch of zeros that you need to delete, okay, then you highlight the ones you want to delete, like this, and then right click, which on the Chromebook is 2 fingers at the same time, okay, and you are going to delete those cells and shift up, and that will bring up the ones from below, okay, and not leave you any blank rows or any blank cells. Okay, so that's how you do that if you're needing to delete data just piecemeal. Okay, since you guys are only going to have 4 runs, okay, obviously I'm just going to delete this column because I'm not going to need it. All right, so now I've got my time and my velocity data. So now I just want to highlight all of that. Okay, go to Insert, Chart. Okay, it always picks the wrong one. Okay, I don't want that. So I want to go to where it says Line Chart. Click on that and go down to Scatter Plot. Okay, and when you do that, then you get this set up the right way. Okay. Now that that's set up to be the right kind of chart.
Can you just wait a few seconds?
Okay, I'll wait a few seconds. Okay, so now that I've got it as a scatter chart, okay, I'm going to go to Customize. And that's where I can change things like my titles, right? Like right now, my vertical axis doesn't have a label, right? And obviously I want it to be velocity. Okay. And I want to change my title. Because right now it's run 1 velocity meters per second, run 2 velocity meters, which makes no sense. Okay, so I'm going to change that to something that makes way more sense and isn't so long, like Newton lab, velocity graph, something like that. Okay, and then I need to get best fit lines for each run. So I go down here to Series,
open that up. Hopefully it already defaults to apply to all series. And then you're going to go down here to these check boxes, and you're going to check trend line. And when you do that, it draws a trend line for each one of your runs. And you can see these have exactly the shape that we expected they would. Okay, run 1 has the lowest slope, run 2, run 3, and so on. Okay, so it goes exactly the way we thought it would. And then I'm going to go further down to label and make it the equation. Okay, so right in here, under label, I just go to use equation. Okay, and you can see now my legend says run 1, okay, and the slope is 1.22 meters per second squared. For run 2, it's 2.4, which makes perfect sense. I have twice as much mass, or twice as much force. I should have twice the acceleration. Okay, and then in run 3, okay, I got 3.5, which is close to 3 times my original value. Okay, and then in run 4, 6. Okay, so not too bad. Okay, it's about 4 times greater than what I started with. Right, so it's following the pattern I thought it should have. Right, so those are my accelerations. Those 4 numbers are the numbers I'm going to need. Now, this graph also needs to go into your lab report, so you would copy it and paste it over into your lab report. Okay, those 4 numbers, the 1.22, well, your numbers are going to be different. Okay, but those are the accelerations, the slope of each graph. Those are what's going to get used to go in this row here. Okay, and to be used to calculate your net force. So you'll take the mass of your system, which is this number plus this, which you only have to do once because your system's mass doesn't change. Okay, multiply that by the acceleration, and you've got this number. Multiply that by the acceleration, you got the number. Okay, everybody with me there?
So the blue cards are the first number?
Yes, the blue cards are the ones that are 270, and the red cards are 274.
Which card did you use when you were measuring your data?
I don't remember.
Okay, should we just pick one then?
Yes. It really won't matter.
Yeah.
Yeah. Okay, now let's talk about the analysis here really quick, guys, because this is actually now like the first 3 steps, the first 3 questions in the analysis. Okay, so question number 1, that's the graph. Okay, we built the graph, done. Okay, calculate the applied force value and record it in your table. All right, so I just take this number here, okay, my 0.50 kilograms, and I multiply it by 9.81, and I've got my applied force in newtons. Okay, so I do that for each of the 4 trials. Acceleration, all right, I record the slope of each of my 4 lines, put it in those boxes. Okay, and then that's it. Okay. Now, for 4, 5, and 6, these are the ones where you actually have to write something in the analysis. Okay, question number 4 is asking, what's the relationship between net force and the acceleration of the cart? So what I'm looking for here is, when net force went up, what happened to the acceleration? Okay, was that pretty linear? Okay, I was just looking at my data, and I was like, okay, here was my original value. My second value, where I had twice as much force, was twice the acceleration. My third one, I had 3 times as much force, and it was almost 3 times. That was pretty linear looking. You got to look at your data and see it's pretty linear. Okay, and then for number 5, draw a free body diagram to describe the forces involved. So 5 and 6 go together. Okay, this is where you need to look at your net force and your applied force numbers. Theoretically, if this was a perfect system, the applied force and the net force would be equal. Okay? In a perfect system, those 2 numbers would be equal because the only force that's supposedly driving the cart is gravity pulling on the hanging mass. Except this is the real world. There are other forces involved. So what you have to look at is my net force bigger or smaller than my applied force? Okay? Because, like we said here, theoretically, those 2 numbers should be the same. Okay? My applied force should equal my net force. But if my net force ends up being smaller than my applied force, that means there's something else
that's working for or against my applied force? Against. Okay? Does everyone kind of follow me on that? Okay? If F net isn't equal to FA and it's smaller than FA, there's a negative force working against FA. If F net is bigger than FA, then there's an assisting force. There's some other positive force going in the same direction as the applied force. Your challenge will be to try and figure out what those forces might be. We mentioned a couple. Okay? If your ramp's not level, see, I said ramp again. If your track is a ramp, thus not level, okay, what force is always present on a ramp? Not necessarily friction. F parallel. Right? F parallel could be present. It could be present either way. Okay? If your ramp ended up being an incline, F parallel would have been working against the applied force. If your ramp was this way, it would have been working with the applied force. And friction could be present in either situation. Right? You have to determine, based on your two numbers, what you think is the most likely situation, and then draw a free body diagram of that. Okay? Better than mine. Okay? And then for number 6 is basically explain your diagram. Why did you choose these forces? Why are they on your diagram? Okay? Everybody follow on that? Okay. Then, same as always, conclusion, copy and paste your hypothesis, okay? And then explain why your results and analysis can support or refute it. Hopefully accept it, because Newton's second law is, after all, law. Okay? It should happen all the time. And then your evaluation, 2 sources of error. We talked about a couple of those. There are those other forces, okay, that could possibly be there, or anything else you think might have contributed to getting slightly wonky data. Okay? And remember, you got to give me ways to improve those or fix them. All right. Any questions on the rest of it there? All right, because you still got like over a half an hour, okay, to work on the lab report and get a lot of it done. Okay? If you got other questions, just let me know. Yeah.
So for the trend line, do you want it to be like linear?
Yes, it needs to be linear.